Good evening, guys. So today's topic, as you know, is factorial design. So we have just completed the single factor design, where we only study the result of a single factor, a single input variable, and we measure the output variable. Give me 1 second. Okay, so a factorial design happens when we have multiple inputs. So the input variables are more than one, minimum 2, maximum any, but practically we limit like 3 or 4 max, because otherwise the interactions will be more. Interaction is an effect of one input factor on the changes made by another input factor. So if you are studying the factors that affect, let's say, the height in a village. So one might be parents' total income, definitely, which reflects on the food intake. Second might be number of siblings, for example. So now you have two factors. Now those two factors might be having an independent effect, might have interactions where one of those effects and the differences because of the other factor, things like that. I think it's not that difficult to understand. Basically, you have more than one input, that is the independent factor, independent variable, and the dependent variables change with respect to more than one independent variable. So we'll learn quickly what are the key terms in this whole idea. One is a factor. What is a factor? A factor is an independent variable. An independent variable is the input to the study. The output is the result. This, I think, by now everyone knows. So in this case, a factor is called an independent variable, or rather, we call every independent variable as a factor. And then we have something called main effect. Main effect is the simplest effect of a factor on a dependent variable. So let's say in this case, we are changing the number of siblings in the study. So how is the output? That is the height of the person, or weight of the person, or BMI of the person, whatever we are measuring. How is that changing with respect to your first factor? That is the main effect. Now, the third term that we are interested is interaction. The conclusion based on the main effects of two independent variables may be at times misleading, unless we take into consideration the interaction effect of the two variables also. According to these guys, McBurney and White, interaction means when the effect of one independent variable, one factor, depends on the level of another independent variable. So another factor. So you have minimum two variables. One changes, the output changes, we measure that. But when we realize that if the number of siblings is 2, the effect of family income on BMI of the kid is this. But when the number of siblings is more than 2, the effect of family income is a little different. Not exactly what the previous study indicated, it's a little different. So there's an interaction. So we learn what factors are, we learn what main effects are, and we learn what interaction is. Now there are three types of interaction. One is antagonistic. The main effect of this kind of interaction is that there is no difference in one compared to the other one. So you have two factors. One, both of them does not change the readings because of the other factor in any fashion. They are kind of independent. Then we have synergistic and ceiling effect interactions. Synergistic is when higher level of one independent variable enhances the effect of other. So the more, so it's kind of a adding effect. When more of one variable is having more effects on the second variable. A ceiling effect is just the other way around. When higher level of one independent variable reduces the differential effect on the other variable. So plus or minus, if there is no interaction at all, antagonistic. If there is a additional effect, it's synergistic. And if there's a reducing effect, like a negative correlation, then ceiling effect. Now, I'll give an example which will clarify these things just in a minute. When you do all this kind of research, we do a couple of things to make sure that we are getting similar readings across all interactions, all possible treatments. If you remember the treatment word from the previous class, what's a treatment? A treatment is a subdivision of all the possible combinations of inputs. So let's say we have, okay, I'll probably have to dance a little with you. So we have two variables for your family income above poverty line, below poverty line. You have two variables for number of siblings, two or less, more than two. So this gives you 4 crossing points. 4 of them are called for different treatments. So now if you're studying in a class, the families or the kids who have less than 2 siblings and who are below poverty lines, there will be one treatment. Same kids above poverty line will be a different treatment. More than 2 siblings below poverty line will be one treatment. More than 2 kids above poverty line will be the 4th treatment. So there are 4 treatments possible. So when you select these groups or treatments, you use these 2 techniques to make sure that you get a kind of a, let's say, decent enough, not leaning towards kind of a sample. Randomization is the process by which experimental units are allocated to treatment, each of the treatment. That is by a random process and not by any subjective process. The treatment should be allocated to units in such a way that each treatment is equally likely to be applied to each unit. So we spoke about this in the last class also. One of the process to make sure that there's no bias in the selection process is to assign a random token or a user flip a coin method or something like that, so that the sample is selected in a random fashion. Blocking. This is a procedure by which experimental units are grouped into homogeneous clusters in an attempt to improve the comparison of treatment by randomly allocating the treatment within each cluster or block. So you create blocks to study. Within that block, you do some randomization. Again, another way of making sure that we are getting homogeneous input sample sets to run our experimentation. Simple 2-factor design, that is exactly what I was showing here, but we'll have it in a different layout here. Factor A, factor B, very simple. Factor A have 2 levels. You might remember the levels. Factor B have 2 levels. That means a factor A, I mentioned one example, number of siblings, up to 2 siblings, more than 2 siblings. Those are the 2 levels of one factor. Second factor, poverty line below or above. Those are the 2 levels of this factor. So A1, B1 is less up to 2 siblings below poverty line. A1, B2 is up to 2 siblings but above poverty line, and so on and so forth. This is a 2 into 2 matrix, easy to see. And similarly, we can have a 2 into 3 factor design that will look like A1, B1, A2, B2, A3, A2, B1, A3, B1. Then this is easy to understand, right? Is it clear to everyone, or do you want explanation? Hand up, thumbs up. All good so far?
Yes, all good.
Okay. Now, example of a factorial design, which I have already given, but we'll go through the example that we have here, which you are also already familiar with: queued recall and free recall. If you remember from the last class, we spoke about the single factor design, in which this was a good example, queued and free recall. Now we are adding one more factor to it. How does the sample set perform if we introduce one more variable? What would be the variable? Number of words. So we conduct the same experiment, queued and non-queued recalls with 12 words, 24 words, or 48 words. Okay. Now we have 2 into 3 matrix. So for queued recall, for 12 words, this is the number of average recall. Queued recall again, 24 words, we have 13. Queued recall, 48 words, we have 19. So similarly, now we get a 2 into 3 matrix, right? Once you get the idea of this cross population of these treatments, it's very easy to understand. Any questions? No. Cool. So I'm skipping through all this. These are all exactly the same thing that I was already mentioning. Now, how do you represent the interaction in a graphic form? This is little new, so I'll go through this in detail. We take the fictitious one data to present fictitious data to present the result in a graphic form. One independent variable is the task complexity with 2 levels. So task complexity, one is very high complex data task, one is a simple task. And second independent variable is level of arousal, which is low arousal and high arousal. And the independent variable is average time to completion of the task. And in that study, this is a table. High arousal state, we conduct the same task complexity, simple and complex task. So with a person with a lot of excitement to get the task done, we get this kind of timing. So simple task was done by this guy in 7.6 seconds. Complex task was done in 13.1 seconds. Now we took any kind of a task, and depending on the person's level of arousal, we again measured the number of seconds it takes for the person to do the task, and we got those tabulated. Then we study this matrix one. Task complexity, simple, complex, low and high, and then we do the reading again for both of them. So now we have some kind of an interaction chart. Here, these were kind of independent studies. Depending on task complexity, we are picking one arousal state and measuring the timings, which is here. Study one result, simple and complex, 7.6, 13.1. So it is increasing. So we know that as the task complexity increases, the time taken to complete the task increases. In this case, depending on the level of arousal with the task, then was actually almost the same time, 10.3, 10.4. That's why you see both of them were taking the same 10.3 and 4. So which means on its own, the level of arousal does not change the time taken to do the task drastically. Okay, now when we plot this, the arousal state versus the complexity, we get something like this. Level of arousals here. So simple task, low arousal is 9. And simple task, high arousal is 6.2. So simple task, high 6.2 and low 9. Okay, so again, similarly, complex task 11.8 and 14.4, 11.8 and 14.4. So this is the way in which you graphically represent these values. So looking at this, you know that immediately that there is nothing much change depending on the time of completion on level of arousal. It's very easy to understand this, right? But the time complexity changes drastically when the task complexity on its own changes. Also, when both these parameters are changed together, then you get something like this. So it's easy to understand from this how these changes happens. Now there is a way of reading this. Whenever these two lines are converging, that means there is an interaction. That means there is an interaction between these two factors, the task complexity and the level of arousal. If there is no interaction at all, these two lines will be in parallel. And mostly in any of the cases, it won't be in parallel. Usually for all practical purposes, they'll be converging somewhere. So let me give you some more textbook context. The concept of interaction can be understood clearly by looking at the graph rather than table, right? So here you can see that interaction is happening because it's converging. The graph for study 3 shows the interaction between task complexity and arousal. The fact that the two lines on the graph for the simple and complex task groups are not parallel to one another suggests that there's an interaction. Whether the lines diverge, go away, converge, come together, or even cross, whenever they are not parallel, the variables interact. If they are parallel, then the relationship between the independent variables is an additive one. Of course, in an actual research study, the lines would rarely be parallel. There will be always some kind of a relationship. Any factor will be affecting the other factor somehow. There are statistical tests that can tell us when they are close enough to parallel, because getting exactly parallel for reading, because we are reading on humans, is going to be extremely difficult. But how much deviation can be acceptable as parallels? There are tests we can run, statistical tests we can run to figure that out. As well as when they deviate enough from parallel to indicate that there is an interaction. Now, importance of interaction. Okay, see guys, we are almost closing down on this chapter. Okay, the last chapter was a decent enough prelude for this. This is just an extension of the last class of single factor design, and most of the pieces I think I have covered already in that class. So if you want me to slow down, let me know. If you have questions, please ask. So let's go to the importance of interaction. The main effect is an average effect. Main effect is an average effect. It can be misleading when an interaction is present. When interaction is present, we should examine the effect of any factor of interest at each level of interacting factors before making interpretation. The two-factor design is really made up of several one-factor experiments. So each of the treatments, you can consider that as a single-factor design. The two-factor design is really made up of several one-factor experiments. In addition to main effect, the factorial design allows us to test simple effect. For example, we had 2 into 2 design. One factor A has 2 levels, and if you read this, it will be confusing. I'll rather go back to the column and tell you what it is. So in this, if you take the readings across this 9 and 6.2, you can get an average across this, and you can say that the output of the time taken can be averaged for simple tasks as the average of this column. The average of time taken for complex tasks can be taken as average of this column. Similarly, if you want to take in it for the raw values, for low arousal, you can say that the average is this average. For high arousal, you can say that the average is adding all this and dividing it by number. Okay, so if you remember in one of our readings, we had taken a reading like this. I think it was for ANOVA or something, when we are adding this way and this way. Remember, there is some kind of a statistical studies that Praveen has already taken class for, where we take the row wise and column wise averages. This is similar to that. So that is the main reading that we get, average. Cool so far? This entire thing is explaining this, whatever I said just now. Sometimes researcher is more interested in interaction than in main effect. For example, a study involving 2 methods and learner of low and high intelligence is an example. Research already established that individuals with low intelligence learn more slowly than individuals with high intelligence. The researcher may not be interested in confirming the results because they already know that if your IQ is low, you will study fast. slow. If your IQ is more comparatively, you will definitely learn faster. But the researcher may be interested to explore whether the relative differences in effectiveness of two teaching methods, let's ignore that and let's say Chavanaprash for low IQ group and high IQ group, is the same for slow learners and fast learners. That is related to the question about the interaction between learning and learning ability. So if you give same amount of Chavanaprash to low IQ group and high IQ group, how does the IQ levels and Chavaprash's availability or non-availability interact? So you might be getting into a result where when low IQ people eat Chavaprash, their IQ drastically increase. When high IQ people eat Chavaprash, their IQ also increase, but not that drastically. Something of the sort. So basically, you are not interested in the general IQ levels of this group, the general, what is it, result of learning speed compared to IQ. You know it for a fact already. Or you also know that Chavanaprash given versus marks taken, that also probably you know that Chavanaprash helps, so marks will be more. You are not interested in that kind of direct reading, the average reading, the main effect. What you're interested is in the interaction between the two. For the IQ levels and availability or non-availability of a Chavanaprash, how does the marks play out? So sometimes researchers are interested in things like that. Question about the interaction between, okay, it could be that method and learning ability interact to such a degree that one method is more effective with slow learners and other is more effective with fast learners. So instead of Chavanaprash, they give an example of two different methods of teaching. So you can end up in a result that this way of teaching is good for low IQ people. This way of teaching is good for high IQ people. Or in IQ people, you can change it as kids from English medium school and let's say local language medium school. Cool, so far? Good. Types of factorial design. Within the subject, the other one is between subject and mixed factorial design. These three, and that's pretty much how class is. And all these three we have covered already in the last session, but I will go through those one more time. What is within subject? Within subject is an experiment by Gordon and Badley in 75 on memory. They hypothesized that memory should be better when the conditions at test are more similar to the conditions experienced during learning. Means if you are having fever and you prepared well for the exam in spite of having fever, when you are actually writing the exam, if you still have fever, your chances of recollecting everything is going to be more. Make sense? So the ability for the brain to remember things are more when they are tried to remember those things in the same setting where you did the encoding of the memory. This has been actually proven. So basically, if you have a schedule that you study from the same table, same times every day, etc., this is how it helps your memory. Instead of randomly here and there picking any time for studying, etc., if you have a very nice schedule and a nice specific place to study, specific way of studying, etc., that's how you tend to learn things faster. Anyway, so that hypothesis was tested using people who can swim. So the underwater swimmers were given this experiment. They were given words to learn under the water and recollect it in the beach or under the water. So now we have 4 sets again. Where did you learn it? Under the sea or in the beach? Where do you recollect it? Under the sea or under the beach, over the beach. So that gives you 4 treatments. And then let's see what happened. The divers were asked to learn a list of 50 unrelated words either on the beach or under the sea, under 10 feet of water. The divers were then tested either on the beach or the sea. The divers were tested in both the environment in order to make sure that any effect observed could not be attributed to global effect of one of the environment. The first independent variable is the pace of learning under the water or outside the water in the beach. There's 2 levels, under or over. The second independent level is place of testing. It again has 2 levels. One is under the water, the other one is under the over the beach. So if we view 2 into 2 matrix again, each subject in this experiment was tested. Now we have 6 subjects here. So A1 and A2 are the 2 levels of one factor, that is for studying, and the B1 and B2 are 2 levels of the second factor, which is where the recall was asked. And we have 6 subjects. So what happens in a within subject? All these people will undergo all the tests. That is within the subject, every subject. So you can see that S1 has taken all the 4 iterations. S2 similarly has taken all the 4 iterations. All of them underwent all the 4 conditions. Okay. So in this, S1 was asked to study those letters under the water. He was asked to recall it under the water. Then he was asked to study it. So this was in beach. Here he was asked to study it under the water and asked to recollect it inside the water. So all the 4 combinations he had to go through. Definitely he was given 4 different set of words. Otherwise he will remember them. Now between subject, how do we do that? We make sure that we get different people for each of the experiment. So it's 1 through 3, 4 till 6, 7, 8, 9 to, so up to 6 people were taken for the first experiment, that is in the beach studying, under the water recollecting, and another set went to the on the beach studying and on the beach recollecting. So all the 4 experiments were given to 4 different set of people. Okay, and that would be called between subject. Okay, so first one is within subject, second one is between subject. Now we have mixed factorial design also, where everything is same, but you will see that for all the variations of A, that is recollecting in beach, was done by same set of people, but in different conditions. Let's say we have this is recollecting, this is learning. So learning is under the beach, inside the water, in an aeroplane, or on a hillside, 4 different types. But for all these things, the people, all the that were doing this test, were all doing all the 4 of them. They were all asked to recollect it always on a beach. Understood? Now you want to also study recollecting on underwater for these people. So what we did, same experiment, we asked the people to recollect under the water, but where did they learn them? In all the 4 situations: in the beach, this 4, on the hillside, this 4, and the water, this 4, and this 4 would be wherever the 4th condition was. So you can see that it's not like everyone had their own conditions. It's not like everyone went through every conditions. Everyone went through some conditions, entire levels of some condition for a single factors, one level. So far clear? That is called mixed way of selecting your sample. So we have between subject, within subject, and mixed, 3 ways of selecting samples. Cool. Now advantage and limitations of factorial design. We'll quickly cover that up, and we should have covered the entire chapter. Factorial design enables the researcher to manipulate and control two or more independent variables simultaneously. By this design, we can study the separate and combined effect of number of independent variables. When it's number of independent variables, it will be like 2 or 3 max. If you have, let's say, 20 independent variables, which is quite possible to have, but then measuring and charting and studying all this is going to be extremely difficult. Factorial design is more precise than single factor design. By factorial design, we can find out the independent or main effect of independent variables and interactive effect of two or more independent variables. The experimental result of a factorial experiment are more comprehensive and can be generalized to a wider range due to manipulation of several independent variables in one experiment. Those are all the advantages. What are the limitations? Sometimes, especially when we have more than 3 independent variables, each with 3 or more levels are to be manipulated together, the experimental setup and statistical analysis becomes very complicated. Imagine you have 5 into 5, 25 types. Now you have to get 25 people for each of these treatments, 25 into 25, 625 people. Then you have to figure out who is good, who is bad, who is possible, etc. So many statistical combination permutations. In factorial experiment, when the number of treatment combinations or treatments becomes large, it becomes difficult for the experimenter to select a homogeneous group. Easy to understand, hopefully. That covers the entire content. Now I am open for questions. And before that, let's stop recording. Ritika?